phone a friend. Make somebody else answer my question.
It's Devin. I'm going to say that the math flow is going to act as a nucleophile in this reaction because you have that negative and then the negative and then mg is the +2.
There's the part. So you're right, and the magnesium is going to flow away because it's a metal. It's a +2 charge, which means when we actually look at this structure, it's better to see this structure as CH3 minus those electrons located on the carbon, and then our magnesium Cl with the positive on the magnesium. Because that's an ionic bond, carbon's more electronegative than the magnesium. Those electrons in that bond are associated more with the carbon than they are with the magnesium, which means the better representation for our answer is indeed the one with the carbon. And the one with the magnesium doesn't make any sense. Okay? This should look kind of familiar. If we react this with HCl, our electrons come out, react with the hydrogen, break the Cl, and I now get my structure with no pi bond, and that hydrogen is now connected. Where is the hydrogen connected?
Hold on. 1, 2, 3. Position 3.
Oh crap, you're running nomenclature on me? Did you do your nomenclature right? Where's position 1?
To the right.
Good job. You probably did that one, huh?
Oh.
They're the same, so it didn't really matter. So 1, 2, 3, yes, your hydrogen should be here. Okay. Why did you do that?
Number it? Or
Why did you place the hydrogen there?
because that carbon now is going to be missing its octet.
That other carbon, position 2, should be a carbocation. The carbocation is more stable at the more substituted position, so it makes sense to put the hydrogen there. When we're going through and running the logic kind of behind that alkene reaction, it's the same as we're doing for officially the Grignard reaction. We called it Grignard, right? Did we call it Grignard? Good. As the reaction shown in the active question, we could predict where the hydrogen would go if we drew out a resonance structure, negative and positive, that we want the positive charge at the more substituted position. Okay, so what we're saying is the electrons are more stable here. We're doing the exact same thing with that bond. We're saying those electrons are more stable on the carbon than they are on the magnesium. Okay, so it's the same logic, but it looks weird, and we tend to stumble over that. Okay. Good thing, you got the right answer, regardless of whether you acknowledged how those electrons were moving. So your instincts are there, which polish some of the explanation. Theoretically, the explanation is not that big of a deal because all you got to do is get your instinct right for the multiple choice, right? Okay. So I would bet, I'm hoping that we did enough kind of background work that your instincts are set correctly and that you'll instinct into it. If I asked you the why, you will probably crumble. Okay, that's fully understandable and appreciated. Like, you should crumble. You haven't spent the time to look at each of those. But what we tried to build up was a reflex that gets you in that pattern. You just may not realize that that's what you've done. Make sense? Okay. Other questions within active?
I'll have more on Monday.
Oh, I just made the questions today.
I did as many as I could.
You're made of questions?
Yeah, I just made a question.
Okay, so what do we got? 7 or 6? Active.
7. Okay, 18.
So some of these are, again, trying to get you to recognize the patterns that we talked about in those other things, and we mentioned names of what some of those functional groups are in the hopes of kind of helping you sort of memorize it. So when we look at the structure that's given, do you see a functional group?
I don't see any pi bonds.
You're right, there are no pi bonds.
Like,
It's not what I asked, but that's okay. what functional group do you see here? It's not a common one, so it's what I would argue an advanced functional group, and it's an advanced functional group that we literally just finished talking about.
Is that oxygen with the 2 carbons and ether?
So if we look, the carbon, oxygen, carbon is absolutely an ether.
Okay.
Yes. This is not an ether functional group.
Oh,
Why is it not an ether functional group?
you need something on that other carbon?
Nope. In red, classified in red, you could absolutely call that an ether functional group. The molecule is not an ether, though. The molecule is not an ether for the same reason that if I look at this structure, I don't call that an alcohol, I call it a carboxylic acid. I don't call that a ketone or a carbonyl, I call it a carboxylic acid. I brought 2 functional groups close enough to each other that they affect each other. So when we go through and look at the question kind of in concern, we have a second ether functional group immediately connected to it. Okay, so this is 2 ethers linked at the same point. Okay, so that purple carbon now becomes extra reactive because it has 2 electronegative elements connected to it. So it's not going to be an ether. What it ends up getting called is
Diether?
nope. Diether is still, you're still calling it an ether. Those are now independent functional groups. Just like here, I don't call this a carbonyl and an alcohol, I call it a carboxylic acid. So the name pretty much entirely loses that meaning. Okay, I can call a diol a system or a diether if they're far away from each other, that they don't affect each other's chemistries. Because they're affecting each other's chemistries, we're changing the name entirely.
Is that what an ester is? No? Okay. I don't know.
As I can help.
Acetone?
It's an acetal. These are our carbohydrates. You're looking at a carbon that has connected out to 2 oxygens. Okay, within that same family of chemistry, you get your hemiacetals and you get your hydrates. Okay, I would group those all in the acetal family. Okay, why does that become important to us? If we've acknowledged that we've got an acetal, hopefully that triggers that our acetals aren't particularly stable. They go to the hemiacetal and then they go to the, it's not hydrate, hydrate's a separate class. They go to the structure that has 2 bonds to an oxygen.
Carbon.
So what happens in this case, I'll draw out a very crude mechanism here in a second. But if we went through and dealt with this system, we'd get our carbonyl there. I think I've got the right number of carbons. There's our purple carbon. Okay. And so what happens in this particular scenario, if we back out to the reagents that are listed here, we have TSOH and H2O. TSOH is a fancy way of saying H plus in the presence of H2O. What happens is our oxygen will pick up an H plus, and because nothing else is really mattering out there, I'm going to just draw that structure. With our H plus, that's an H, dang. Okay, the oxygen doesn't want to be positive, so what does it do? It takes the electrons, leaving behind a positive carbon. That positive carbon in and of itself wouldn't be particularly stable, except we have the other oxygen there that can resonance stabilize it. Okay, that's temporary only because that oxygen would then carry a positive charge and I can't get rid of a carbon easily. Okay? The more permanent fix is where I bring in that H2O. That H2O is what comes in, reacts. I now have my carbon bonded to my OH with my positive. I'd have this OC. I'd lose one of those hydrogens to make it a neutral oxygen. Then I protonate again over here. That's positive, acts as a leaving group, forming my carbocation. The electrons come in. Okay. And you're like, oh my God, there's way too much happening in there. You're right, there's a lot happening in there. Okay. And since you made the face at me, what we'll do is back out of this entirely. And we will go to where it appeared. Our acetal, okay, there's the carbon, what I was calling the purple carbon, our red OR, and then our blue OR. Okay, and what happens is we backtrack out. What did we do? We protonated. Okay, once we protonated, that could then leave, giving us the carbocation. Once we had the carbocation, we could have water come in and attack, okay, forming that positive oxygen. The oxygen doesn't want to be positive, so we ditch a hydrogen. We get to the hemiacetal. Then what happens is we protonate. Those are the same. We protonate. Okay. That now acts as a great leaving group. Leaves, we get to here, positive. We ditch the hydrogen and we go back. Okay. So what that particular active question is doing is flipping the script on this. So if you look through at this diagram, you might be like, well, but those arrows aren't saying that, because what are these arrows showing the formation of? They're making the acetal. What the question is asking you is unmake the acetal. Go from the acetal back to the carbonyl. So what you could go through and do as a decent example for practice is erase all of these arrows. And now add arrows to the structures to go from the bottom to the top. Okay? So if we were to start down here, how do I go from here to here? Well, I have H plus, my electrons go to there. We protonate to go from here to here. What happens? That acts as a leaving group. There's that structure, my carbocation. How do I go from here to here? We're bringing in H2O. The electrons come in. There's my H2O. Okay. Because the focus isn't on going in this direction, those bonds aren't always explicitly shown. What happens to go in the next step? We take those electrons, put it back onto the oxygen, and we get to our hemiacetal. Everybody see that? So what you should be able to do is backtrack this mechanism. Okay, note those arrows, if we look at our arrows, they all go both left and right, which means you should be able to go both directions. Okay, because of how our mechanisms are intentionally designed, we read from left to right, effectively top to bottom. And so if you're trying to follow a mechanism using curved arrows, it's always going to run left to right. So if you want to say, well, how do I do the reverse? You've got to remove all of those curved arrows and now say, how do I want to backtrack through it? Does that make sense? Okay. For the sake of this question, this is where we could shift to the far summary on the right. You're not expected to crank through that whole mechanism all the way through. Okay. What you should be able to do, which is where I was trying to push you initially, was to recognize the initial functional group. We had a carbon with two oxygens with R groups, okay? And then what did we react it with? Well, the rest of the question said H2O. So what do I have? Well, I have an acetal and water. What happens with an acetal and water? Boom. Goes to the carbonyl. So I eject those and I draw the carbon-oxygen double bond. Net result, I started with two oxygen bonds. What do I end with? Two bonds to oxygen. It's the same thing, it's just what oxygens you're making those connections with. Does that make sense?
Yeah.
Okay. And so what you're trying to do is do that pattern recognition and find all those pieces. You haven't had a whole lot of time. Okay. If we think through pattern recognition, that takes time and practice. You don't have a lot of time and practice. Okay. And for those people who know, well, why didn't you give us more time and practice? Then that means you lose the understanding stuff that we talk through. It's a give and take. Okay. There's way too much content to cover, and it's just going to come down to how we want to look at those patterns. Kind of make sense?
Yep.
So, and that is a different question. And it's one that gets uber specific into our actual reagents. There's not a whole lot I can do about that because that's forced within each of those systems. If you see things like that on active or on the homework, usually what is TSOH? And what I would do is tell you, oh, that is a source of H+. Okay? That's really all it's there for. If we drew out those structures, maybe you'd be able to see that. But I get the feeling that if we actually draw out the structure for TSOH, you'd get a bit overwhelmed. And you'd be like, oh, that's ridiculous. I can't figure that out. Right? Well, let's simplify it. And instead of saying that's that, let's call it, let's just make it another OH. Are you still overwhelmed? No, you're not overwhelmed? What are we looking at?
What do you mean?
What is that?
I don't know the name.
I bet you do.
Maybe I do know the name, but I don't remember the name. Oh.
That's sulfuric acid.
Okay.
Okay. So what is TSOH? It's sulfuric acid. It's sulfuric acid, except instead of one OH, we replaced it with a ring. The activity of it is still sulfuric acid. It still has this very acidic hydrogen. Why did we replace it with this big old purple thing, or with that thing in the purple box?
For fun.
It's not for fun. How is that different from OH?
Has a lot of resonance.
Yes. What kind of bonds are present? Touche. Answer that question again, but not using sigma and pi. Not that direction either, because that's just trying to rephrase your sigma and pi.
What do you mean?
There's another very important bond classification system that you should be using. It's how we predict almost all of our chemistries.
Polar.
Those are not polar covalent. Those are non-polar covalent, which means their intermolecular forces are London dispersion. If we consider most organic molecules, when we look at our reactions, what is the vast majority of that reagent? Non-polar covalent. If I threw sulfuric acid at it, would I expect the sulfuric acid to mix? No, because the sulfuric acid is all hydrogen bonding / ionic, and my compound is all non-polar covalent. They would never mix, and if they never mix, they don't react very well. So what do? I modify the structure so that I now have some non-polar covalent bonds so that they mix. Because they mix, I get more activity within the reagent system. Okay, that's again pushing to the deeper level behind OChem, which is why I would argue saying TSOH is a bit obnoxious. It's uber specializing the reagent. We don't need to do that. Okay, it's just I've got limitations. Okay? When it comes to the final, what I will try and do if I see a question that says TSOH is delete TSOH and write H+. Write what it's actually acting as, because that's the more relevant part to me. You will not remember any of these reagents, but if you can remember any level of the functionality on how they react, I count that as a massive win. You may not, but I do. Make sense?
Yeah.
You said full of questions.
Didn't we need to go over the aromatics?
You want me to finish the EAS stuff? Yeah, we can do that.
And I can also ask you questions on Friday.
EAS, officially, I don't have any more slides with it. It's all from the PlayPosit. So really all we're going to do is talk through it, and you now have an opportunity to kind of interject and be like, oh, wait, what does that mean? What does that mean? What does that mean? And we can kind of address those things. And then the other part that I will do is delete things and say, I don't want to ask that question. I don't want to ask questions about that. Okay. So the big thing, what we'll do is walk through the initial PlayPosit. If we're talking about electrophilic, what are we looking for? A positive charge. Okay? If we're talking about aromatic, this is a bit of a stretch for us because we've never really defined what aromaticity is, and I think it's beyond the need for this class. The classic example of an aromatic structure is benzene. So if I drew out benzene, okay, would I expect that to act as a positive?
It could.
Why?
Resonance.
Okay, yes, there's resonance. Okay, but what are those electrons doing in that resonance? So if I move those there, I would generate a negative and a positive. What would I do to stabilize that forming positive or that forming negative?
Move the one next to it. And just move it.
Which does what to the positive?
Moves it.
It gets rid of it altogether. Okay, or it just constantly moves it around the ring, so I don't have a static positive, I don't have a static negative. Okay, which is going to get to kind of the next aspect behind this. Okay? If we push out to something that we've seen before, how did that reagent act in purple?
It shared its pi bonds on the positive.
Which means it was?
Which was, the pi bond was a nucleophile?
It was a nucleophile. Okay, so what I find interesting is that when we say this aromatic, you're like, oh, it can act as a positive. And yet when I go out and show just a single double bond, you tell me it acts as a nucleophile. Okay? The nucleophile still had that resonance option within it. Okay? Or sorry, our alkene still had that resonance option within it to put the negative in the positive. The aromatic ring has resonance to stabilize it all, which means what happens to the strength of the either positive or negative within it becomes massively weakened, because those electrons are shuttled around the ring, which means the aromatic ring we would expect to not react, either as an electrophile or as a nucleophile. If we force it to react, how might we predict it? Well, we should initially go back to chemistry we already know. And if we go through and look at this, since those are non-polar covalent bonds, those electrons are equally shared between it. I don't generate a strong positive or negative. All I generate is a higher energy source of electrons in the p orbital. What does that mean? How would I predict benzene to react?
As a
It's most likely as a nucleophile. We've got a whole lot more electrons in it than we have for a standard alkene, and our alkenes reacted as nucleophiles. So our benzene structure should act as a nucleophile. Why is that useful for us? We said electrophilic aromatic substitution, and we said the electrophile was positive. Is it likely that our benzene is going to be the positive? No. Which means this positive thing needs to have some kind of identity. This is where I call it just E for electrophile. Okay? And if I'm now going to complete this out, or as far as the statement goes, we're looking at a substitution. A substitution means I run a chemical reaction where I exchange two things for each other. Right? Well, when I look at the benzene, I only have carbons and hydrogens, and then I've got whatever E is. So E has to exchange for something within here. What's the easiest thing for it to exchange for?
pi bond.
A pi bond is an exchanging out, because an exchange means like for like. That's an atom. What's the most likely atom I can exchange out for? Hydrogen. The carbons are embedded within the structure. I would have to break a whole lot of bonds and then reform a whole lot of bonds. Not very likely. So it makes more sense that what I'm doing is I'm exchanging out a single hydrogen for an electrophile. That single hydrogen in the replacement will likely come out as H positive. Why should it come out as H positive? It's not likely to take the electrons, because where are the electrons going? Into making the bond with the electrophile, which means we're going to do a full swap, balance our charges. If we're now going to predict out a mechanism, we would take the electrons from our pi bond, react with the electrophile. What this is, whoa, that is a horrible looking hexagon. I only drew one line. Okay. We would form a positively charged structure here. This structure is necessarily going to be significantly higher in energy, all because of that particular carbon. What is special about that particular carbon? the green dotted one. Okay? There are 4 groups of electrons. There was initially a hydrogen there. Okay? So that structure is tetrahedral. Why does that matter? Okay? Well, I form a carbocation, I want to stabilize it. I need to move electrons. So what I can do is start drawing a bunch of resonance structures to explain the stability of that carbocation. And what I will find is that I cannot resonate all the way around the ring because the hybridization of that particular carbon. That carbon blocks the resonance going all the way around the ring. That makes this intermediate less stable. These structures could get called tetrahedral, but we've used that term already in a different mechanism, so we try to be less repetitive, and we remove that term, and you almost always hear reference to them as sigma structures. Sigma structures because what kind of bonding do we have at that special carbon? Only sigma bonds. The rest of them have pi bonds also, okay, or at least some pi capability. Right? The last step of the reaction, we want to reform our pi bond by removing the electrons from that carbon-hydrogen bond, and we would get to our final answer. Kind of, sort of? Okay. That's the process of electrophilic aromatic substitution. So when we go through and address this in the larger sense, what we have to do is now add some specificity to it. Okay? And there's 2 directions of specificity that we address. Number 1, we look at the electrophile. Okay? Here, this was just in a generic E, something positive. Okay? So anything that's positive could potentially run this reaction. Okay? How do we get those positives? That's now looking at the specific reagents, and we'll look at that in a second. Okay? The aromatic ring itself should not react. Right? If we drew out that resonance, positive and negative, but I can do more resonance to stabilize that all the way around. So we'd say the aromatic ring doesn't react. So what does that mean? We have to make that E positive very positive. So we almost always have to add some kind of catalyst to speed the reaction along. What that catalyst is doing is making our positive more positive. So when we look at an initial structure, we might be like, well, I don't see a positive or a negative. But if we add something else to it, that can force our positive to become more positive. If we can make the positive bigger, stronger, that makes this reaction more likely to occur. The other thing we can do is tweak the aromatic ring. We can tweak the nucleophile by making sure it has more electrons. That one becomes a harder one to tweak. Okay, for the electrophile, to make it more positive, what do I got to do? Take electrons away. Pretty easy to just take things away from people. Okay? But if we look at the benzene ring, what I'm trying to do is put electrons in. Can I put electrons into the benzene ring? Why not? What did you get for shaking your head? Yeah. When we look at the benzene structure, all of the octets are already, where are you going to put more electrons? Okay? And that becomes kind of the dilemma when we look at our aromatic ring. Okay? And so ultimately what we go through and do per people in the lab is that we change the whole dynamic. So I'm going to erase everything. And when we look at our benzene ring, what we just discussed, God, why can't I draw a hexagon today? When we go through and look at that benzene ring, all of those hydrogens are identical. This can happen in any particular case. So to speed our reaction along, what we have to do is tweak the aromatic ring. And instead of having a hydrogen on there, I'm going to modify it to have some other atom. Okay? And what I want that atom to do is to somehow affect the ring. Okay? Well, if I'm trying to make the reaction go faster, I need more electrons in the ring, which means what does atom X need to supply? It needs to supply electrons. So we could start at the example of, let's give it a pair of electrons. And if it has a pair of electrons, what could it do? Well, it could share them into the ring. What happens when we look at our resonance structure? What charge do we just build on the ring? A negative. So if I can modify my benzene, okay, starting instead of just straight benzene, start with something else where I have some unknown atom that has these electrons, it makes my ring more active. It makes it more nucleophilic because it can make it negatively charged. Okay? Drawing a lone pair makes it really easy, but what we can do is kind of back away from that. All we need to have is more electrons than what? We said benzene was slow. We just need more electrons than, not benzene, hydrogen, because that's the only thing we changed. Okay? So our comparison just says, do we have more electrons? So what if atom X was oxygen? It has more electrons. Okay? But if I did that, would oxygen be happy? No. But we don't really care how oxygen feels. We just care that oxygen can donate those electrons in. Okay? What about carbon? This one becomes a strange one.
That doesn't have electrons to donate in unless you deproton.
That carbon does not have electrons to actually donate in, but we have to remember back to what our rule was. It wasn't that we actually had electrons per se, it's that we had more electrons.
Oh,
More electrons than what?
one?
Than hydrogen. Does carbon have more electrons than hydrogen? Yeah. It can't actually donate through resonance because we exceed octets. But because it has more electrons than hydrogen, it can share kind of some of that electron density through sigma intermediates, okay, to make the ring more active. Is it going to be as active as if I then... I think I just need to reset on all those words. Which ring would be more active, green or blue? Blue because
More electrons.
they don't accept more electrons. And we'll look at why in just a second. Say that? Because it has resonance. So it's not that it has more electrons per se, it's that it is actually able to do resonance. Okay? And I said the more electrons is kind of an irrelevant argument, so let's drop in one more. So we've got now 3 new benzene structures. We could call them red, blue, and green. Which of those would we expect to be more reactive? So it's talking about the ability to make the ring negative. So what we might go with is which one makes the least sense to make it go faster? The carbon, because?
Still doesn't have
So it's not, again, not the number. There it is. It's not necessarily the number of electrons. It's that it is incapable of doing resonance. Both the bottom structures have the ability to do resonance. Okay, so that makes both of them go faster than our carbon. Okay, and why do I want you to avoid the number argument? Because if you use the number argument, which of these goes faster, blue or red? Blue. But it's not true. Okay, and we can come back to the why it's not true. Where you looked was good. Okay, maybe it was just random, but where you looked was good. Okay, the other thing that I would kind of push on is that when we think about how it activates by resonance of how many electrons? Just 2 electrons. I don't care how many sets of electrons I've got. As long as I got the 2, I can do it. That's all that matters. Okay, so this has 2, that has 2. I could only donate 1 pair at any given instant anyway. There's no difference in the amount, okay, or the ability of the amount. So Shay, where were you going when I was trying to say how would we differentiate those? What were you looking at? Periodic table? Okay, why? What are you looking at on the periodic table to decide which of these should be better or more reactive in an EAS reaction? Okay, you can say, I don't know, that's fine. It's absolutely awesome to be looking at the periodic table to figure this out.
Oxygen doesn't want to donate as much because it's more electronegative.
There it is. Oxygen is more electronegative than the nitrogen. What does that mean? Right? When we're talking about the ability to share electrons inwards, what we're talking about is, again, the reactivity of the ring. Okay? The rings are constant. We care about how the atoms outside the ring affect it. We're looking at a molecular effect. This is resonance. Okay? Both of them can do resonance. Okay? But oxygen, being more electronegative, is less willing to do that resonance than the nitrogen. Which means nitrogen is now the most active in this particular scenario. Kind of, sort of? Cool. We're going to backtrack out a little bit more. I want to go back to the generic X structure. Okay. So by modifying our benzene ring, we can now speed the reaction along. Okay. Or we could speed the reaction along as long as that atom X had more electrons than our hydrogen. What if that atom X had less electrons than hydrogen?
Doesn't it slow it down?
Why would it slow it down?
Because you are looking to do an electrophilic substitution.
Why does putting an atom X with a positive charge make the ring less nucleophilic?
Because it's positive.
What's positive?
The X.
Why do I care about atom X? I don't care about the ring.
Because you want to donate electrons.
What are you saying, Lee?
It's on the outside.
No, still don't care.
You want it to donate electrons in.
Why can't I take these electrons and donate them to an electrophile? Why can't I do that? Because I would argue I absolutely can. 100%. Fair game. Wouldn't X want the electrons? Yeah, so you mean wouldn't those pi electrons resonate this way? What would that result in if it did that? Pi bond to X? That doesn't help me. I would form a carbocation on the ring. What did I say the ring needed to act as? A nucleophile. And nucleophiles are negative. They have electrons. By putting an atom X on the ring that has less electrons than hydrogen, I'm pull electron density out of the ring, making the ring positively charged. That's why when we talk about these modifications, we want things that have electrons to shift in. Okay? Just because we want that doesn't mean that's the structure we're given. We could be given a structure that pulls them out. Okay? So what would that look like? Okay, well, atom X in this case is nitrogen. Does nitrogen have more electrons than hydrogen?
Yes.
You might say, well, yes. Does this nitrogen? Hydrogen has 1 electron, which means its charge is 0. No, this nitrogen does not. It's actually missing electrons, which is why it's formally positive. Okay? So one thing we can look for is that atom X, does it have an explicit positive charge on it? Okay? When drawn out in this Lewis form, it makes it easy to see that, yes, that's positive. That fits in that X category where it's missing electrons. Though very commonly, what you would see that structure written as is NO2. Do you see a positive? Do you see a negative? No, so you would have to know the Lewis structure drawing of how that builds out to recognize that.
But if you were like drawing that structure, wouldn't you draw it with 2 double bonds to each oxygen?
So, in pushing to that, I would say you should try that on your own.
Okay.
No, it doesn't work. Okay, you're going to run into octet issues. Okay? If we look at this, does atom X have more electrons or less electrons than hydrogen? Maybe like, I don't really know, you haven't specified all those bonds. Okay, so let's specify some bonds. More electrons or less electrons than hydrogen? Why more? When you look at this pi bond, what could you do with that pi bond? I could do resonance. Where would I move those electrons? Where would you move the electrons in that pi bond? Why would you move them to the oxygen? Why would you move the electrons in that pi bond to the oxygen and not to the carbon? Oxygen is more electronegative than the carbon, which means those electrons belong up towards the oxygen. Whoops, I actually already drew it there. Which then means what charge is the carbon? Positive. Damn. So what happens here? Atom X has less electrons than hydrogen. It's just buried behind a resonance structure, making it hard to see. This is why we always have to be considering resonance when we go through our reactions and be like, what could that resonance do? That resonance can help you predict. So when we talked all the way back to the beginning, we talked about resonance, we talked about best and useful. Those useful ones show us that chemistry that aligns to things that we might memorize. The best ones make everything look nice and pretty, but then they hide that chemistry, so it makes it harder to see what's happening. Kind of make sense? Okay. So now let's genericize it even more, because we said we could have atom X either be positive or negative, but now let's just say X. I don't care whether it's positive or negative. If we've made this modification, this is necessarily going to introduce another potential issue. When we ran the EAS reaction initially, which hydrogen did I substitute? Any one. Why?
Because they're all the same.
They were all identical. It didn't matter which one I took. Is that still the case? Nope. They're now all different from each other. Or not all different from each other, but they have some patterns that could come out of it. This hydrogen is going to be different from this hydrogen because they're a different distance from atom X. This hydrogen is also different. Again, different distance, directly across from X versus next to. Okay? When we shift over to the other side, this, oops, that's not supposed to be an X. Maybe that's why you gave me a funny face. This hydrogen is identical to that hydrogen. They're the same distance, just on different sides. Think arms versus legs. Same deal with the other one. We could then go through and reference those based off of a nomenclature system, counting them out, 1, 2, and all of that. Okay. Our 1 would be where our atom X is. 2, 3, 4, 5, and 6. So we could reference the purple ones being at 2 and 6. We could reference the blue ones at 3 and 5, and the purple one, the black one at 4. Okay? That involves numbers, and organic chemists are allergic to numbers. So of course we invent words to describe those locations, and we would call this one ortho. Okay? Organic chemists also then go through and call this one meta, and they could call this one para. So that now when we talk about substitutions with an atom X on there, we can reference which hydrogen we're removing based off of its relative position to atom X. Or we could reference an absolute based off of nomenclature systems with doing a proper numbering. Which we choose ultimately comes down to a flip of the coin on whichever process someone saw better. Okay? How great are most organic chemists at nomenclature? Complete and utter trash. Okay? This is one of the reasons why we should kind of abolish it, because nobody uses it appropriately. Okay? So you almost always will hear reference to ortho, meta, and para. Problems with ortho, meta, and para is not only are chemists allergic to numbers, we're also allergic to letters. This is why everything is lines. Okay? So there's way too many letters in ortho, so instead I call it O. Meta, M, whoops, I forgot a color, and para, P. So you could hear reference to the numbering system. You could hear reference to ortho, meta, para. You could also see OMP. Okay? So now we know that they're different. How does atom X affect this? Okay, well, that atom X, how it affects, has a lot to do with the identity of atom X. If atom X was positive, what happened? The electrons got pulled out, right? And if atom X became positive, we see a positive charge build on the ring. We would see a positive charge build at the ortho position. Okay? And if you continue to draw resonance, you will find that it will also build at the other ortho position. Okay? And if you do resonance, you will also find it builds at the para position as well. Okay? So if we were to abbreviate this, we could draw partial positives there, and we have to show partial positives because we drew the double bonds. Okay? Where would I expect the substitution to happen? So this ring should go slower, but if I throw a wicked strong electrophile at it, I can make it react. Where would I expect the substitution to happen? What does the ring act as in an EAS reaction? A nucleophile. And to act as a nucleophile, what must you have? Electrons. And what electrons do you have at the ortho and para positions? A complete and utter lack thereof, which means don't do it at the ortho or para positions. Instead, do it at the meta. So if we look at atom X being less electrons than hydrogen, it should slow way the hell down, and it should only do substitutions at the meta, not at the ortho or the para. Kind of makes sense?
Yeah.
Of course, what does that mean we should also look at? What if atom X had electrons? What would those electrons potentially do? Donate inwards, drawing a resonance structure. Where we put a negative charge at the ortho position. If we continue to manipulate all of our resonance, we would note that we get a partial negative charge, formal negative charges at our other ortho and at the para. Where would I expect the substitution to happen now? At the negatives, which would be my para or ortho. So if atom X has electrons, I get substitution at the para or ortho positions. If atom X is missing electrons, I get substitution at the meta. Okay? So this is why it becomes valuable to understand our resonance, because all we got to do is manipulate the resonance through to see how that propagates to understand our chemistry. That's lovely. Okay? Or what we do, since we've walked through all of that, we could then go through some attempt at a glorious summary and say, you were good with all that, right? Could I delete it? Okay. Oops, I won't even do that. We'll do this. If atom X has more electrons than hydrogen, faster reaction. Because we like transformers, we can call that atom X, we can call it an activator. Right? The end. Doesn't that remind you of transformers? Whatever. Okay. Or our substitution would happen at the para and ortho positions. If atom X had less electrons than hydrogen, we would expect this to be slower. Again, transformer reference. D activators. And we would expect our substitution to happen at the meta position. Okay? Now I don't have to do any of the resonance if I've memorized all of that. Lovely, right? Okay? You got a crap ton of stuff to memorize. This is why I would argue we deal with the resonance so that we can not have to memorize as much. Okay? You've got to decide your line. Kind of, sort of? Okay. Are there exceptions? Yes. There is one nasty exception. What if atom X is a halogen. If I made atom X a halogen, let's call it bromine. Does bromine have more electrons than hydrogen? Yes. Is it willing to share those electrons? No. So if we look at it, bromine, yay, I have more electrons than hydrogen, but hell no, I'm not giving you. Which is it? Is it the activator camp or is it the deactivator camp? Why not both? It's a deactivator. It will slow the reaction down, but it directs para and ortho. So it sits right in the middle and takes a little bit of each of those categories. Okay? Kind of, sort of? That covers kind of the fundamental of what's happening on the nucleophile side. The other part is now looking at what all the electrophiles are, and there's a ton of potential electrophiles. And that's what the... sorry, you were still writing that. And I don't have a way of bringing it back easily. Do I? No, I don't. Whoop, don't do that. Should I draw it all again? I mean, it's in the recording. Recording for your notes, 50 minutes. More than one way. Okay, so if we go through and look at this, this is our speeding the electrophiles. We've got a couple different electrophiles. One of the things that you should note within all of these is all of them need to generate a positive. BR2 is that tricky electrophile we've talked about a couple times, right? I think we've talked about that one a couple times. Okay. One of the bromines withdraws electrons, which leaves the other one hanging out as a positive. The nitro should look good as a positive, well, because it has a positive charge. Okay. Last one should look as an electrophile because the carbon's the electrophile because the easiest thing to evaluate is our resonance. It's withdrawing electrons, but we can also add to the fact that this chlorine is also electronegative and withdrawing electrons. So both of those things together are really making that center carbon very, very, very positive. Okay, so all of those are our electrophiles. We could try and go through and figure out which one was the most electrophilic. Okay, well, which one of those do you think is the most positive? Probably the middle one because it's actually positive. Yeah, good job. Okay, it doesn't have to be hard. If we're going to now look at the other ones, what are we trying to talk about to decide between those two? Well, here it's just a withdrawing effect, an inductive withdrawing effect. What's happening over here? Induction and resonance. Which one's more positive? The carbonyl compound. Okay, so you're recognizing those patterns. It's now trying to build those out. Make sense? Okay. Oh, okay. Sorry, my back is kind of bugging me. So if we go through and look at our electrophiles, we can make them more electrophilic by adding a Lewis acid catalyst. The whole point of that catalyst is to help suck the electron density away. So if we look at this top one, it should be very similar, or it should look identical to the bromine, that chlorine. Okay, the acid catalyst we add, iron as a metal carries what charge? Positive. What could we do with that positive charge? Try to stabilize it with electrons. As that shares electrons inwards, we do formally see a positive there, but does chlorine want to be positive? No, so what does it do? Takes the electrons, which really means the reactive chlorine is the same one all the way through. It's the one on the far left. Even though in our intermediate structure, we had a formal positive charge on that chlorine. Kind of, sort of? But what our catalyst is doing is to help remove those electrons. Okay? That reaction, using chlorine or halogen or any of our halogens as electrophiles, yes, absolutely, I think you should know that. Okay? The electrophile that comes out of that is our Cl positive. So if we were to look at a potential reaction, if you saw Cl2 and FeCl3. What that should be screaming at you is that you've got the Cl positive and you're looking at an EAS reaction. Does that make sense? That's what I want you kind of seeing within this. Okay. Very, very well, it's similar enough that you might be able to pick it up. What we're looking at here is a carbon bonded to a bromine or a chlorine. Okay. Well, carbon bonded to a bromine or chlorine, what's happening to the electrons in that bond? They're getting taken towards the bromine, making the carbon very positive. You mean exactly like what happened above? Yes. Yes, very much so. Okay. That bond doesn't break naturally easily on its own, at least as far as EAS goes, because we need a super active electrophile, which is why we have to add a catalyst. And note, the catalyst is effectively the same thing. It's that metal with a positive charge, a place to dump electrons so that we can make our formal positive at the end. Okay? So hopefully you can see the patterns of those being effectively the same chemistry. We're now looking at an R positive. There are complexities with that one that I will not ask about, okay? But they are there. The last one on here, you'll note, is very similar as well. Okay, again, we've got that carbon with that chlorine. That same polarization is happening. This one becomes extra electrophilic because resonance with that carbonyl is an extra contributor to this process. Okay, this one creates a really fun thing. I like talking about this one a lot. It's probably my favorite ion to reference. Nobody thinks it's very particularly funny, but I think it's a silly ion. It's the acylium ion. Acylia. I'll be here all week. And it's extra special because you can get actually resonance stabilization of the carbocation. Okay. And if you were wondering about tying that back to aldehydes, you can't tie that back to the acidity of aldehydes. Okay. The acylium is positive. When we talk about the acidity on aldehydes, you're trying to make it negative. It's a whole different ballgame. Okay. But sometimes people will reference back to this. Okay, but there's our acylium ion. All of those chemistries would argue doing the exact same thing. You have a halogen, you withdraw the electrons from the halogen, making whatever the halogen was connected to uber electrophilic. There it all is. Okay? We've got the actual electrophilic atom highlighted in red. Oh, never mind. Okay? We've got some kind of extra issues that can come up, which the video talks about. This requires active nucleophiles, and this works with almost all rings. I don't care. We're looking at nuancing the levels of difficulty there. Don't stress about that. In the video, we'll talk through them. This is talking about Friedel-Crafts, and in particular, this one is going to reference the extra complication of this, because if we run this reagent exactly as we just showed, what we should be getting would be that as our positive charge. What is the problem with that positive charge? Well, I need more. I can't. What's that? It's a primary carbocation, so not stable, yes, because it's a primary. And what do we say about primary carbocations? They don't form. Well, we said they don't form. Yeah. We really technically have to shift it to they rarely form. We're following under very particular circumstances to kind of force the formation of it. But they are so unstable that they go through a rearrangement, which is why you get weird stuff. But what did we say about rearrangements? Don't worry about it, okay? So don't stress about the potentials for rearrangements behind those. It is technically there. Again, if you go out into the real world to talk about Friedel-Crafts alkylations, that is a complication behind them. We've talked about it. That's all I really care about. I won't test on rearrangements. Okay? There is some hybridization requirements, again, going back to this, but again, don't stress about it. if we shift now, when we talked about our electrophiles, we said they could be done with Lewis acids. We can also do it with Bronsted-Lowry acids. I do like the first one for forming the nitronium ion, that positive nitrogen electrophile, only because if we go back and look at the chemistry of this reaction, we're taking nitric acid, reacting it with sulfuric acid. What do you remember about nitric acid?
Not much.
I asked nitric, didn't I? I meant sulfuric. What do you know
Oh,
about sulfuric acid?
Very strong.
Yeah, it's a strong acid. What do you know about nitric acid?
Very strong.
Yes, they're both strong acids. Okay, if you went through 151, depending on your instructor for Chem 130 or even 152, you might have actually been told to memorize both of those are strong acids. Okay? And one of the things that you might have experienced in going through those general chemistry courses is that what happens when you mix an acid with an acid? Good answer, nothing. Okay, we would say nothing happens. And yet, in this case, something happens. Why does something happen? Sulfuric acid is so strong as an acid, it can make another strong acid act as a base. That's wicked. Like, that's pretty neat. Okay? So nitric acid accepts a hydrogen. That makes this water that doesn't want to be there, so it takes the electrons, leaving behind our positive nitrogen. So that's why that reaction is neat. I like it. I just spent some time on it. I can't guarantee I would ask a question about it on the test. More than likely what I'd ask is, what's it acting as in this reaction? Just because you should be able to predict that. Make sense? In fact, I can almost guarantee that's going to be a question.
You're asking what's the nitrogen?
Yeah.
What was
If I gave you this reaction, I could ask, what is HNO3 acting as in this reaction? Acid-base nucleophile electrophile. And actually what I would ask is, what is nitric acid, HNO3, acting as in this reaction? Being intentionally misleading because it says nitric acid, so of course it's acting as. No, it's acting as a base. Look at your reaction. Make sense? See, look at that. You know one of the questions of the exam now. Right? This can happen with sulfuric acid. Sulfuric acid is a strong acid. It can make sulfuric acid react with itself. What's exciting about that one? Absolutely nothing. Don't worry about sulfuric acid. Just ignore that one. Okay. Last one, I think I do kind of want you to know because it fits some other chemistry. We'll take sulfuric acid again, except this time we'll react it with an alkene. Okay. Why would I want you to know this one?
Because it's an addition.
This is an acid addition. This fits all the way back to older content. Okay. And in the previous cases, we always followed it up with some kind of nucleophile that immediately came in and reacted. Why did we not talk about aromatic rings coming in and doing it? Because that chemical reaction is not super clean and easy, right? That's why we saved that part for the end. Okay? It still fits the same basic patterns of our electrophile addition that we talked about. That's why I think I actually want this one on there, because it's now kind of a repetition. We talked about this, see how it's valuable? We could keep using it. Make sense? Hooray!
Yeah.
So, you have successfully made it through all of me yabbering at you for an entire semester. Congratulations, good job. I apologize.
And now I'm going to go rewatch all of it.
We still have time, so we can still go through and answer other questions you've got. Officially, you still have lots and lots of time because I'm not going home till 4:30. I would just plan to move to the tutoring center, so if you still had questions, you could follow up there. But I don't think I want to stay in this room officially. Okay? Maybe because I have food in the other room for me. So, if you don't have questions, you're welcome to take off. If you still have questions, go ahead. What do we got?
17. I thought I understood it, but it wasn't like what I thought I understood.
Major product of this under aqueous conditions. Okay, so the aqueous conditions is technically a hint for us. What does aqueous mean?
Water.
Water. What do you see?
Water.
Water and
And oxygen.
a carbonyl. We're looking at hydrates. Okay, so it's not going to be an acetal or hemiacetal because it doesn't do that with water, it does it with an alcohol. Okay, but hopefully what we would see within this, and maybe I'm screwing it up, we'll find out here in a second. Okay, those electrons would polarize out. There's our positive, there's our negative. We could take a look at water, HOH. There's a positive, there's our negative. What should we do? Hook them up, erase the stuff in between, and we would get our answer. Which is officially a hydrate. Because what did you do? You added H2O to the structure. You've hydrated it. That's quite literally what they're referencing when they call it that.
Okay.
Make sense?
Yep.
There's a potential they're asking for something more than that, and I'm not sure if they are.
No, I submitted it.
Oh, okay. Next.
21.
This really bugs me how small that font is. I need to yell at them. They need to make that bigger. Does it look bigger on anybody else's stuff?
I was zooming.
Ah, it's ridiculous. How do they not look at that and be like, oh, that's ridiculous. Why don't we make that bigger? Must be. The freaking young people, jerks. Okay. So this is broken into two steps. So focus on our first step. That first step will make a little bit bigger. Sodium, NH2. Okay. So if we're focusing here, we've got our reactant in purple and our reactant in red. What we want to do is try and find the most reactive thing. Where's the most reactive thing? Red or purple? Sorry, purple. Which is most reactive, red or purple? Okay, what do you see in purple?
Possibility of resonance.
Possibility of the resonance, so we get a positive and negative being partials. What do you see in red?
Well, I said residence is
Okay, well, that's what she said.
You also get partial sign.
No, you do not get partials on the red, which is why I don't like you saying purple.
You get full charges on the red.
Sodium is a metal, which means we're looking at an ionic bond. This isn't partial charges. This is a full transfer of electrons. The sodium gives up all of its electrons to the nitrogen, making the nitrogen negatively charged.
And the hydrogens.
Okay, and those hydrogens could be partial positive. Okay, to them being partial positive or formally positive, okay, they're at best partial positive. Okay, because if that nitrogen shared its electrons, so if we said, okay, there's that negative, there's a positive, and we react this, what do we get? Oh, that bugs me that it's not on the grid. I can't believe I did that. Right? Why are you shaking your head at me? What's wrong with it?
No, I was feeling hair on my face.
Okay, that's fine. I don't know why I need to give you permission for that. Okay, so it's possible. What's special about that carbon? It is tetrahedral. Is not chiral. It's symmetric across that because of the wedge dash. We have to remember that tetrahedral part. What can you tell me about oxygen?
It's negative.
In general,
It's electronegative.
it's electronegative. What can you tell me about nitrogen? Electronegative. What you've effectively built is our acetal family. What was the issue with our acetal family? What's that? They're not particularly stable and they tend to revert back to the carbonyls.
Oh.
Okay, so we're in a little bit of a gray area here trying to figure out what's going on. So what we could try and do is say, okay, well maybe we just push forward. What do we see in the next thing? A lot of carbon and hydrogen, which would mean theoretically you are blurring your vision and not looking at the carbon and hydrogen and instead looking at that carbon and bromine at the very end. And what is that carbon bromine at the very end setting you up with? A partial negative and a partial positive on that carbon, which would then mean you could run the reaction where you have a negative react with a positive. Do we have a negative? On the oxygen. So why not go through and say, okay, let's change that and now put the carbons, 1, 2, 3, 4 carbons. There's 1, 2, 3, 4 carbons. Can you see how we got there?
Yeah.
Okay. In a show your work, I would actually probably be okay with that, as it's not right. Okay. But what you've done is followed those negatives and positives kind of all the way through to the kind of natural ending. Okay. The part that you missed, whoops, wrong eraser, is that our sodium amide here, yes, is negative, but it is so negative that it wants to neutralize as fast as humanly possible. Because we're talking about fast, when we're talking about accessibility. What's the most accessible thing?
What do you mean?
Hydrogens.
Oh.
Hydrogens on the outside are more accessible than the electrophile on the inside. Do we have any acidic hydrogens? Technically 4.
Oh.
We have the alpha hydrogens. The alpha hydrogens are roughly the same acidity as water. We're trying to neutralize that charge as fast as possible. What we end up doing is in our very first step, instead of creating that monstrosity, we create this one with a negative charge on the carbon. That negative charge on the carbon is better than on our nitrogen due to resonance stabilization and all of that, okay, but not formally done. So what do we need to stabilize that negative?
Positive.
What do we have in step 2? We have a positive on that carbon. So we could take that negative electrons, have it attack our positive carbon. What happens? We're now forming a bond between our negative carbon, call that a green line, to our blue carbon, 1, 2, 3, 4, representing all of our 4 carbons. Kind of, sort of. The big thing that stands out, and I know this is not a big thing that stands out for you, I fully understand and appreciate that. It's really going to come into that very first step. If we're looking at a neutral nitrogen, it's not very reactive, so it'll attack the carbonyl. If it's coming in negative, that's reactive, bro. You need to quench that as fast as possible. That's going to be now acting as a base, not as a nucleophile. And that's a very subtle distinction to make within that system. If you see a negative nitrogen, base. You see a neutral nitrogen, nucleophile. Okay?
So basically like to have more charge. In the
They both like to be charged.
Okay.
What it's coming down to is effectively how stable they are as charged.
Okay.
If you have a negative nitrogen, while electronegative, isn't the most electronegative, so it's trying to offload that negative charge as fast as possible. It would rather offload it to a hydrogen, because then it forms this nice neutral NH3, than offloading it into the carbon. It has to effectively get past the hydrogens to get in there. If it was NH3, neutral nitrogen, why would it pull off the hydrogens? You'd be forming a negative. Relative stabilities aren't going to align.
Maybe that's confusing.
Yeah. I'm looking at it, and for whatever reason, I never saw the nitrogen attacking the carbonyl. Didn't even cross my mind. And I'm trying to think of ways that you could see that short of just rote memorization. One way you could see that is look at your answer choices, because it's multiple choice.
Yeah.
I think that's probably going to be your best bet. If we're going to have that nitrogen act as a base, almost universally, you're not going to see the first option we drew up. I think I can almost actually guarantee that. Think, actually, almost guarantee. Yeah, those don't all go together very well. Okay? We are officially at time. Again, if we've got more questions, I'll stick around and answer, but you don't have to stay here.
What it was. It looked like what you were there, with the four carbon.
Give me a sec. I think I can show the answer here.
I pretty much showed exactly what you did.
I don't want to retry. Give me my answer. There it is.
Oh, okay.
1, 2, 3, 4. Yeah.
Got it.
You could and should be able to draw it on the other side also. And it shouldn't flag that as being wrong. Doesn't mean it doesn't, but it should.
14 is for me.
Oh yeah, that one. I looked at that. I'm like, what is going on with this?
I've tried.
I haven't even attempted it yet. I was like, I'm not even gonna look at this. Not right now.
Oh, it isn't horrible. This actually fits kind of nicely in the last system that we just looked at. Okay. HCl gets you really just H plus. H2O gets you electrons. So what we're looking at is our oxygen effectively being our partial negative. Okay. If we go back and look at this drawing up above, okay, what is our central focus thing that should be jumping out at us? You're right with positive nitrogen. I wanted pi bond first, but you're absolutely right with positive nitrogen. With that positive nitrogen, what's going to happen? It's going to take the electrons from that. And so if we did that, what happens? We'd have a lone pair on nitrogen, but more importantly, we have that positive charge on our carbon. So what could happen? Our oxygen can come in. Okay? And so what you should be seeing here is that we're looking at that polar pi bond. And this goes back and forth. So if I want to go this direction, I need to add the nitrogen. If I want to go that direction, I just need to add the oxygen. Why is that relevant? Well, I look at the question, what do I see? I see the positive nitrogen, but again, that wasn't my primary emphasis. The primary emphasis was that I have that pi bond to that positive nitrogen. What I'm starting with is this structure. There's a whole bunch of other trash. Trash, don't worry about it. Okay? And what do I see in the reagent? The O. So what do I want to do? I want to convert that double bond nitrogen across. Where we potentially run into an issue is how this splits. But the resonance allows us to see that. Okay? So what we should be seeing, putting it on a stupid grid. I need to zoom in on the grid so I stop drawing it so small. Is that we would get our double bond oxygen replacing, right? What happened to that dash stereochemistry? Did I do anything there?
The one at the top?
Yeah.
Yeah, it stays the same.
Stays the same. What happens at the other end? Well, I'd get the nitrogen. Oof. Man, I'm really botching these hexagons today. Okay. That nitrogen is then going to leave. What happened to all the hydrogens of my water?
Stay on. Oh, they won't.
Okay. That nitrogen would come out positive. So it doesn't have to become positive. We could lose one of those hydrogens out there. But what we'd end up getting is these two kind of systems.
So the
Okay.
nitrogen's gonna leave?
Nitrogen will leave the structure.
How did it do that though?
Do you want a mechanism?
Should I know the mechanism, or should I just know it does that?
So really, remember, at this point, you're responsible for just the answer. You're not going to be asked to draw a mechanism. So if you can look at this and be like, I understand this pattern right here, you're fine. You don't need a mechanism. If you want to understand how it does that, what you're asking for is a mechanism. All I'm trying to do is that actually what you want? Because if you want it, yes, I'll do it.
I want it.
Okay.
Because I really don't understand it.
Yeah.
I really do not understand it.
This is going to look a little bit weird. Do you all have questions, or are you just hanging out to see what happens?
A little bit of both. We wanted to double check the finals Thursday, right? Is that what we all decided? Or are we
Either.
Tuesday or Thursday.
Tuesday or Thursday?
It's up to you.
11 a.m.
And
Yep, 11 to 12:50. We're so gonna regret asking for this. How detailed do you want?
I just want to see how that other bond breaks. One of the nitrogen. It's like this. Oh, it just breaks the other way.
As I'm drawing, if you want to stop me at any point because you got a question, please do. I think I can squeeze it in. I may regret that.
All those proteinaceous.
Yep. That's why I said you were gonna regret it.
Honestly, I don't regret it.
It makes more sense.
Because I really did not understand that.
It's just so much like that.
You might regret me asking.
I'm used to drawing it. Actually, it's not that.
Are you still recording this?
Yep.
Oh, that's what I was going to ask.
Yeah, the silence I'm sure is gonna be awesome. Someone's gonna be like, oh, he's just drawing. What happened to the audio? I don't hear anything, and like turn it up max volume. If somebody did that and they're listening, I apologize. I think I got it right.
That makes so much more sense.
So, and this is in the, officially, if we go through and actually look at each of those reaction arrows, they're equilibrium. And that's, I think, where most people struggle with these, is that it's hard to acknowledge the backwards and forwards of each of those reactions. So it's hard to say, well, why is it going forward? It's going forward because we've imbalanced the reagents to bias it towards one direction versus the other. Mechanistically, it can go either direction, and it's going to sit at an even balance effectively between them. How you get it to go towards the carbonyl versus the imine structure is going to be pretty much solely dependent on the presence or the lack thereof of water if you want it to go towards the carbonyl, or the nitrogen if you want it to go towards the imine.
Okay.
So you would change those concentrations relative to each other to force which direction you go. Unfortunately, when you look at a question, none of that is obviously stated. It's all based off of lab work. So what you're left with is at the beginning, and you just have to assume that you're set in that system. Can I clear this? And
Yeah.
go back to the question? So that when we go back to the question and we look here, what you're assuming is that we've got the double bond nitrogen, we've got our imine, and we've got tons of water.
Okay.
And really that's all that's happening, is we put tons of water, which then forces that to kind of undo that system. The one thing I'm kind of nervous about, but I don't think they would do, the stereo center didn't do anything, so it shouldn't change. That particular structure has some secondary chemistry that could have manifested, and thankfully it did not.
Okay.
So you don't need to worry about that. But that made me a little bit nervous starting into it, is that stereo center was going to do something.
I just
Thankfully, it
needed
didn't.
to change.
And so this is where, when looking at this question, what I would hope you do is exactly what I asked, and you responded the correct way, but then you probably saw everything else and freaked out. You've got the positive nitrogen in the pi bond. That is the only thing you need to see.
Okay.
And if we look through that whole effed up mechanism that we drew out, that was the only thing that changed, was right there. Nothing else did anything. Okay, but it's easy to see those and be like, oh my God, I've got rings. Oh my God, I've got if it doesn't change, it doesn't change. Don't worry about it.
Because like I saw, if you scroll down, it shows the NH part, but I was like,
Was wondering
how
about
in the
that
world did
actually.
that break apart like that?
Yeah.
So I was just really confused about that.
And that's, again, recognizing that pattern. Where this is coming from within the slides, we did not do a lot. I would almost argue we did no talking about it. It's a little bit better than that, but not by much. It's right there.
Yeah, I was looking at that.
And note, again, when I draw it out here, the only thing that we're really referencing is the nitrogen. This one's referencing the enamine, which is a little bit shaky. I don't think I'd ask questions about the enamine just because that's pushing the boundaries. But that's exactly what we would just walk through.
Mm-hmm.
Is just looking at that detail. And no, it doesn't matter what any of those numbers are, because they weren't relevant to the mechanism.
Okay. For the final, would you say it's like a pretty even spread, like 25% unit 1?
So asking about the final breakdown is a perfectly fair and valid question to ask, and it's one I have zero ability to answer right now.
Okay. Do you think it's heavy on unit 4 maybe?
I have zero ability to answer because
Yeah,
I
okay.
do not have it written.
Okay.
Okay. What I have gone through and done so far is I took, where is it? Of course, I've got the grade book open. That's the part I haven't done yet. I need to do that.
It's gonna do, right?
Yeah.
Okay.
So,
That's gonna go through all the previous tests and review.
yeah, what I was going to show you is what I've done first. I went through, and assuming nobody's in office hours today, that's my plan to go through that. And if people show up in office hours, what I'm gonna do is, we've got these two documents, the old review and the last part. So what I did is took the old review, which has 97 something questions in it, and I went through and just went like, no, I don't want to ask, no, I don't want to ask, no, I don't want to ask, and started grouping things. So I've whittled that down to 50 questions. And then what I'm going to do is take this last part and do the same thing and combine those two documents. And then I'm going to pull open exam 1 and be like, I like this question, I like this question, I like this. And so they're mostly chronological order. So I'll be able to be like, these are questions that I like, and I'll insert those in. And then I'll look at the total number and be like, well, shit, it's 200 questions. It's not going to hit 200 questions. God, I hope it doesn't. And then just start whacking questions out of it, being like, that's too specific, that's not. So ideal breakdown to me, yeah, I'd like to see 25% on the new stuff.
Okay.
It makes up a quarter of our semester. It should be. Though I fully acknowledge you haven't had time to practice that, so what's going in my mind, and it's all based on how much time I've got to actually design the test, is using the older content. I asked you all sorts of individual mechanistic steps. We've gone through and talked about individual mechanistic steps for all of these. So what I could do is show an EAS reaction and say, what's this mechanistic step? That's kind of fourth unit.
Yeah.
It's kind of not. So I think I would classify that as fourth unit because it's forcing you to look at the content from the fourth unit, but in the context of our second unit. Does that make sense?
Yeah.
So to me, that question I would qualify as fourth unit. You may qualify that as second unit because that's where you saw it initially.
Okay.
Does that make sense?
Yep. So you're taking everything from the old review, the last part doc, and all of the old exams? Okay.
Yep.
So focus-
Ideally, I write new questions.
You don't have to.
I don't think it's likely.
Yeah.
Is all it comes down to. I just don't think I've got time.
Okay.
Admittedly, there's that acid-base one with nitric acid and sulfuric acid. I don't think that one's in any of those. I have that question written somewhere else. So that's an easy one for me to drop in. I just have to copy and paste it.
Okay.
But that's probably the only new question at this point.
Okay. What room are you gonna be in at Pecos campus?
Oh, for
Friday and Monday?
Friday and Monday, if it's library 228.
Okay, so it's the same one that says on the office hours.
Yep,
Okay.
exactly.
I'll be there on Monday.
Yeah, so if you go in the main library doors, up the stairs immediately turn towards the right. The room is immediately right there, but you have to go down the hallway to get in the door.
Okay.
Um,
I've been staying at my cousin's house lately.
so you don't have to drive as far?
No. Cousin, my uncle passed away.